On August 14, 2003, a seemingly ordinary summer afternoon transformed into a scene of unprecedented chaos across the northeastern United States and parts of Canada. Without warning, lights flickered and died, elevators ground to a halt, and traffic signals ceased their rhythm. Millions were plunged into darkness and confusion, a stark reminder of our absolute reliance on a power grid we often take for granted. This wasn't a natural disaster or an act of sabotage, it was an engineering failure, a chain reaction initiated by an unlikely culprit, demonstrating the profound fragility of an interconnected system. To understand the events of that day, we must first grasp the immense complexity of our modern electrical grid. It's a vast, dynamic network of power plants, transmission lines, substations, and distribution networks, all operating in perfect synchronicity to deliver electricity on demand. Power generated hundreds of miles away can be instantly consumed, creating an intricate dance of supply and demand. This interconnectedness, while efficient, also presents a profound vulnerability. A single disturbance in one area can rapidly propagate, affecting distant regions in a phenomenon known as cascading failure. The morning of August 14 began without incident for FirstEnergy, a major utility company operating in Ohio. Temperatures were moderate, and electricity demand was within expected ranges. Operators in their control centers monitored hundreds of parameters, from voltage and frequency to power flow across their vast network. Like any other day, the grid was humming along, supplying power to millions. There was no indication that a series of seemingly minor, isolated events would, in just a few hours, escalate into a continental crisis, exposing critical flaws in both human and automated systems. The initial trigger for the blackout was disarmingly simple. At 1:33 p.m. Eastern Daylight Time, a 345 kilovolt transmission line, known as the Hardingstar Line, in northern Ohio, came into contact with an untrimmed tree branch. This was not an unprecedented event. Vegetation management is a continuous challenge for utilities. However, the exact location and the critical nature of this particular line in the regional grid architecture turned a routine fault into a catastrophic domino. This localized contact, occurring far from any major urban center, would send ripples through the entire eastern interconnection. The immediate consequence of the tree contact was a short circuit. Designed to protect the grid from damage, the circuit breakers on the Hardingstar line immediately opened, isolating the faulty section. This is standard procedure, a critical safety mechanism. However, due to software anomalies and configuration issues within FirstEnergy's control systems, the operators were not immediately alerted to this trip. The loss of a major transmission line meant that the power it carried had to be rerouted, putting increased strain on adjacent lines. This redistribution of load was the first critical step in the cascade. A critical layer of defense in modern power grids is the Supervisory Control and Data Acquisition, or SCADA, system. This software platform is designed to collect real-time data from across the grid, providing operators with crucial insights into its health. On August 14, FirstEnergy's SCADA system suffered a series of failures. Alarms for the tripped line didn't appear. Critical data updates slowed and eventually stopped. Operators, expecting visual and auditory alerts, were left blind to the unfolding crisis, unable to assess the true state of their system or the escalating overloads. Without reliable information, the human element of grid control became severely compromised. Operators, receiving fragmented and outdated data, struggled to understand the sequence of events. What they saw were isolated trips, not a systemic problem. This lack of situational awareness prevented them from taking timely corrective actions, such as shedding load or redirecting power proactively. Valuable minutes, then hours, slipped away as the underlying conditions for a widespread collapse worsened, transforming a localized fault into an unmanageable crisis across multiple utility zones. As the Hardingstar line remained out of service, the burden on neighboring transmission lines steadily increased. Within an hour, 3 more FirstEnergy lines in northern Ohio sagged into untrimmed trees due to increased current and heat, triggering their own circuit breakers. Each subsequent trip redistributed the load, creating further overloads elsewhere. This was the true beginning of the cascading failure, each protection system, doing its job to isolate a fault, inadvertently pushed the problem onto another part of the system, like pulling a thread that unravels an entire garment. The grid operates on precise frequency, typically 60 Hz in North America, and voltage levels. As more transmission lines tripped, the balance between power generation and load consumption was severely disrupted. Generation sources became isolated or overloaded, leading to a drop in system frequency. Simultaneously, the inability of the remaining lines to carry the redistributed power caused voltage levels to drop across vast areas. These deviations from stable operating parameters are critical warning signs, and if uncorrected, they activate further protective measures, often leading to more widespread disconnections. A crucial defense against a total collapse is under-frequency load shedding, or UFLS. These automated relays are programmed to detect significant drops in grid frequency and, if they fall below a critical threshold, instantly disconnect non-essential loads to balance generation and demand, thereby stabilizing the system. However, in the 2003 blackout, FirstEnergy's UFLS relays were either inadequately deployed or simply overwhelmed by the speed and scale of the frequency drop. They failed to activate sufficiently to arrest the cascade, leaving the grid vulnerable to further decline. As more lines tripped in Ohio and Michigan, large sections of the grid began to separate from the wider interconnected system. This process, known as islanding, creates isolated pockets of generation and load. While sometimes a controlled strategy, in this scenario, it was uncontrolled and chaotic. These islands often lacked a proper balance of generation to meet their internal demand, leading to rapid frequency and voltage decay within them. The instability grew exponentially, quickly spreading from FirstEnergy's territory to neighboring utilities, oblivious to the initial tree contact. From the initial tree contact at 1:33 p.m., the situation deteriorated with astonishing speed. By 4:10 p.m., less than 3 hours later, the entire eastern interconnection began to fracture. The uncontrolled tripping of lines accelerated, leading to a massive loss of generation across multiple states. Over 256 power plants went offline. The system, unable to stabilize itself, plunged into darkness. This was not a gradual dimming, but a sudden, violent cessation of power across an area spanning over 9,300 square miles. The statistics are staggering. The 2003 Northeast blackout affected 50 million people across 8 U.S. states and Ontario, Canada. It brought major cities like New York, Detroit, Cleveland, and Toronto to a standstill. Airports shut down, communication networks failed, and businesses ceased operations. The estimated economic cost alone ran into billions of dollars. This wasn't just a power outage, it was a societal disruption that highlighted how deeply interwoven electricity is with every facet of modern life and the fragility when that lifeline is severed. Restoring power to a system of this magnitude, known as a black start, is an incredibly complex undertaking. It cannot be done by simply flipping a switch. Power plants need electricity to start themselves, creating a chicken and egg problem. Utilities had to incrementally bring small, isolated generators online, then use their power to energize transmission lines, slowly rebuilding the grid section by section. The process requires meticulous coordination and can take days, or even weeks, further emphasizing the delicate balance of grid operations. In the aftermath, a joint U.S.-Canada task force, spearheaded by the North American Electric Reliability Corporation, NERC, launched an exhaustive investigation. Their mission, to pinpoint every contributing factor, from the tree branch to the systemic failures. Their findings were critical, revealing not just a series of isolated errors, but deeply embedded flaws in operational procedures, technological infrastructure, and regulatory oversight. This incident served as a stark, undeniable wake-up call for the entire North American power industry. The investigation highlighted significant human errors. FirstEnergy operators lacked proper training for complex, escalating events. Crucially, communication protocols between different utilities were insufficient. When problems began in Ohio, neighboring utilities weren't immediately aware of the severity or the potential for regional impact. This fragmented communication meant that the opportunity to proactively shed load or adjust generation in adjacent regions was lost, allowing the local failure to grow into a widespread disaster. Beyond human factors, critical systemic flaws were exposed. First Energy's SCADA system, meant to be the eyes and ears of the grid, was outdated and failed spectacularly. It couldn't cope with the volume of events, leading to data freezes and alarm suppression. Furthermore, the lack of sufficient automated safety relays beyond basic circuit breakers meant the grid relied too heavily on human intervention in a crisis that unfolded too rapidly for human processing. The system simply wasn't built with enough redundancy and intelligent automation to self-correct during such a large-scale disturbance. The 2003 blackout served as a powerful catalyst for change. One of the most significant outcomes was the establishment of mandatory reliability standards enforced by NERC. These standards covered everything from vegetation management, ensuring trees are trimmed away from critical lines, to control room operations, operator training, and data visibility. Utilities are now legally required to adhere to these rigorous guidelines, with hefty penalties for non-compliance, transforming grid reliability from a recommendation into an imperative. A key engineering lesson was the need for more sophisticated automated safety systems. The industry moved towards deploying remedial action schemes, or RAS, which are advanced protective relays designed to detect specific grid conditions and take pre-programmed corrective actions, such as automatically shedding load or tripping generators, without human intervention. These systems act much faster than operators, isolating faults and preventing cascades from developing, providing the grid with an intelligent, autonomous defense mechanism against extreme events. Today, the North American power grid is significantly more robust than it was in 2003. Investments in smart grid technologies, enhanced monitoring capabilities, and improved inter-utility communication have made the system more resilient to disturbances. While the threat of large-scale blackouts can never be entirely eliminated, the lessons learned from that summer day have led to profound changes in how we design, operate, and protect our electrical infrastructure. The silent collapse triggered by a single tree branch underscored the intricate balance of power, revealing both its incredible might and its surprising vulnerability.